do some time value of money calculations, and we're going to start with the very simplest, coping with singletons. And I want to introduce you a couple of rules that make it easier to compare items in the future with items in the past. Now, here are the three rules. Just go ahead and lay them out directly. One, you need to compare flows at a common reference time. You can't add money now to money later. It's two different kinds of money. It's like trying to add together dollars and baht. You're just not supposed to do it. So you always have to make some kind of conversion. But what it comes down to is that the reference period, which is rule 2, doesn't really matter. You just pick one that is computationally convenient for you. Now, for the most part, what you're going to start off doing is always thinking about things in future value. How much money do you have in the bank when you are done with the project? And that's a perfectly legitimate thing to do. It's very easy to go ahead and grasp how much money you're going to have in the bank afterwards. But eventually you're going to find out that this is computationally inefficient. Things which are computationally inefficient are oftentimes prone to mistakes. And right now, starting off the class, about 75% of you are going to have this future value point of view. You're always going to be comparing future values. About 25% of you will be easily thinking in terms of present value. By the time this class is over, you'll be virtually all converted over to thinking about things in terms of present value. But again, it's going to turn out that it doesn't matter which particular time period you choose. Choose one that is computationally efficient for you, but also make it something that is conceptually efficient for you too. Make it so it's not easy to get confused. And the final rule that you're going to bump into is that interest rate, that discounting rate that you use, all your calculations based upon that change once you change it a little bit. So if you find that you prefer a future value rather than a present value with a set of calculations with an interest rate, and you alter that interest rate, your decision may in fact change. All of your calculations are undone at that point. Now let me go ahead and show you how that works off in a simple example. And this is that simple exponential time discounting that I showed you, where you take the future value and you divide it by 1 plus the interest rate raised to the power of the time periods that are in the future. So I'll start you off with $100 now. And I'll also give you this other value, which is $126.82 12 months from now. And I'll also give you an interest rate, which is 2% per month. Now, let's go ahead and start off with evaluating each one of these now. $100 now, evaluated now, is really easy because it's just $100. And if you don't believe me, just go ahead and take $100 and divide it by 1 plus 0.02 raised to the power of 0. And that evaluates to a 1 in the denominator, and you should get the $100 back. You can also take that $126.82 and take it from 12 months in the future back to now. And so what we're doing is dividing by 1 plus the interest rate raised to the power of 12, so we're 12 months into the future, and bring it all the way back to now. And you're going to find out that it's approximately $100. There's a little bit of rounding that goes on right there. So what we've established then is when we are evaluating these two bits of money, one in the future, one now, they're exactly equivalent to each other. Now you can also do that at a time period 12 months from now. So what I'm going to do here is take that $100, and if you go ahead and you look at that equation of P is equal to F on 1 plus I to the n, and just move that on 1 plus I to the n part all the way over to the other side, you can see that that's how you're supposed to grow $100 now up to what it would be 12 months from now. So what you're doing here is taking the $100 times 1 plus I to the power of 12, growing up that $100, letting it accumulate interest, and letting the interest accumulate interest for 12 months until it reaches $126.82. And that's the point here of Rule 2. Once you see these two guys as being equivalent, it doesn't matter which time period you use. Even as we see in the examples below, you start looking at it 6 months into the future, or if you start looking at it 2 years in the future. Once you've established that they're equal to each other, no matter which time period you evaluate it at, they are going to remain equal to each other. Now please note, the minute you start changing that interest rate away from 2%, these two things are no longer going to be equivalent. Now, crucial in our calculations, but unsaid, is how we are defining time. Now, you can think of time in a couple of different ways, but the two most common ones to consider is that time is going to be something which is integer valued, so you can have period 0, period 1, 2, 3, -7, or you can have time be continuous. Throughout this class, we're only going to deal with this kind of discrete time. So time can be 0, 1, 2, but we can't have time be 1.23 or anything along those lines. Now you can do it, and there are some applications for continuous time, but those get to be something which are a little bit more advanced. And so if you ever start dealing with optimal control problems, Hamiltonian systems, or anything along those lines, you'll be messing with continuous time at those points. But we're going to stick with this discrete time. Now, it's not as big an assumption as you think it is, because most of the time, yes, we do deal with discrete time. Things that happen early in the month are not necessarily distinguished from being later in the month. If you go ahead and make a purchase on the 15th and you pay for it on the 20th, sometimes there's not interest that's involved there, and it's all considered to be the same period. And we're doing effectively the same thing. We're just saying that anything that happens within a time period is all equivalent to each other and all happening at the same time. A nice way of thinking about it is that anything that happens between the first of the month and just moments before it clicks over to the next month is all the same, and then immediately afterwards is the next month. Now there is quite a bit of notation that's associated with valuing time. I've already introduced you to the interest rate. Pardon me. I've already introduced you to the interest rate I. I've introduced you to P, which is usually the present value, or the value at time period 0. I've also introduced you to the future value, which is usually the value in period N. But we're also going to start looking at a kind of graphical notation about what the benefits are, as well as a symbolic notation. And so I will cut this short screencast to an end while we'll start talking about those items.